A Short Account of the History of Mathematics by W. Ball. Chapter 18. Leibniz and the Mathematicians of the First Half of the 18th Century, Part 4. Cavendish. The Honourable Henry Cavendish was born at Nice on October 10, 1731, and died in London on February 24, 1810. His tastes for scientific research and mathematics were formed at Cambridge, where he resided from 1749 to 1753. He created experimental electricity and was one of the earliest writers to treat chemistry as an exact science. I mention him here on account of his experiment in 1798 to determine the density of the earth by estimating its attraction as compared with that of two given lead balls. The result is that the mean density of the earth is about 5.5 times that of water. This experiment was carried out in accordance with a suggestion which had been first made by John Michell, a fellow of Queen's College, Cambridge, who had died before he was able to carry it into effect. Rumford. Sir Benjamin Thompson, Count Rumford, born at Concord on March 26, 1753, and died at Auteuil on August 21, 1815, was of English descent and fought on the side of the Loyalists in the American War of Secession. On the conclusion of peace he settled in England, but subsequently entered the service of Bavaria, where his military and civil powers of organization proved of great value. At a later period he again resided in England, and when there he founded the Royal Institution. The majority of his papers were communicated to the Royal Society of London. Of these the most important is his memoir, in which he shewed that heat and work are mutually convertible. Young. Among the most eminent physicists of his time was Thomas Young, who was born in Milverton on June 13, 1773, and died in London on May 10, 1829. He seems as a boy to have been somewhat of a prodigy, being well read in modern languages and literature as well as in science. He always kept up his literary tastes, and it was he who first furnished the key to decipher the Egyptian hieroglyphics. He was destined to be a doctor, and after attending lectures at Edinburgh and Göttingen, entered Emmanuel College, Cambridge, from which he took his degree in 1799, and to his stay at the university he attributed much of his future distinction. His medical career was not particularly successful, and his favourable maxim that a medical diagnosis is only a balance of probabilities was not appreciated by his patients, who looked for certainty in return for their fee. Fortunately his private means were ample. Several papers contributed to various learned societies from 1798 onwards prove him to have been a mathematician of considerable power. But the researches which have immortalized his name are those by which he laid down the laws of interference of waves in light, and was thus able to suggest the means by which the chief difficulties in the way of acceptance of the undulatory theory of light could be overcome. Wollaston. Another experimental physicist of the same time and school was William Hyde Wollaston, who was born at Dereham on August 6, 1766, and died in London on December 22, 1828. He was educated at Caius College, Cambridge, of which society he was a fellow. Besides his well-known chemical experiments, he is celebrated for his researches on experimental optics and for the improvements which he effected in astronomical instruments. Dalton. Another distinguished writer of the same period was John Dalton, who was born in Cumberland on September 5, 1766, and died at Manchester on July 27, 1844. Dalton investigated the tension of vapours and the law of the expansion of a gas under changes of temperature. He also found the atomic theory in chemistry. It will be gathered from these notes that the English school of physicists at the beginning of this century were mostly concerned with the experimental side of the subject, but in fact no satisfactory theory could be formed without some similar careful determination of the facts. The most eminent French physicists of the same time were Fourier, Poisson, Ampère, and Fresnel. Their method of treating the subject is more mathematical than that of their English contemporaries, and the two first named were distinguished for general mathematical ability. Fourier. The first of these French physicists was Jean-Baptiste Joseph Fourier, who was born at Auxerre on March 21, 1768, and died at Paris on May 16, 1830. He was the son of a tailor and was educated by the Benedictines. The commissions in the scientific corps of the army was, as still the case in Russia, reserved for those of good birth, and being thus ineligible, he accepted a military lectureship on mathematics. He took a prominent part in his own district in promoting the revolution, and was rewarded by an appointment in 1795 in the Normal School and subsequently by a chair at the Polytechnic School. He went with Napoleon on his eastern expedition in 1798 and was made governor of Lower Egypt. Cut off from France by the English fleet, he organized the workshops on which the French army had to rely for their munitions of war. He also contributed several mathematical papers to the Egyptian Institute, which Napoleon founded at Cairo with a view of weakening English influence in the East. After the British victories and the capitulation of the French under General Menon in 1801, he returned to France and was made prefect of Grenoble, and it was while there that he made his experiments on the propagation of heat. He moved to Paris in 1816. In 1822 he published his Théorie analytique de la chaleur, in which he bases his reasoning on Newton's law of cooling, namely that the flow of heat between two adjacent molecules is proportional to the infinitely small difference of their temperatures. He states that the theory demands that the temperatures of stellar space should be between -50 degrees Celsius and -60 degrees Celsius, a conclusion which it has been as yet impossible to prove or disprove. In this work he shews that any function of a variable, whether continuous or discontinuous, can be expanded in a series of sines of multiples of the variable, a result which is constantly used in modern analysis. Lagrange had given particular cases of the theorem and had implied that the method was general, but he had not pursued the subject. Fourier left an unfinished work on determinate equations, which was edited by Navier and published in 1831. This contains much original matter. In particular, there is a demonstration of Fourier's theorem on the position of the roots of an algebraic equation. Lagrange had shewn how the roots of an algebraical equation might be separated by means of another equation whose roots were the squares of the differences of the roots of the original equation. Boudin in 1807 and 1811 had enunciated the theorem generally known by the name of Fourier, but the demonstration was clumsy and not altogether satisfactory. Fourier's proof is the same as that usually given in textbooks on the theory of equations. The final solution of the problem was given in 1829 by Jacques-Charles François Sturm.
Sadi Carnot. Among Fourier's contemporaries who were interested in the theory of heat, the most eminent was Sadi Carnot, son of the eminent geometrician mentioned previously. Sadi Carnot was born at Paris in 1796 and died there of cholera in August 1832. He was an officer in the French army. In 1824 he issued a short work entitled Réflexions sur la puissance motrice du feu, in which he attempted to determine in what way heat produced its mechanical effect. He made the mistake of assuming that heat was material, but his essay was the commencement of the modern theory of thermodynamics. Poisson. Siméon Denis Poisson, born at Pithiviers on June 21st, 1781, and died at Paris on April 25th, 1840, is almost equally distinguished for his application of mathematics to mechanics and to physics. His father had been a common soldier, and on his retirement was given some small administrative post in his native village. When the revolution broke out, he appears to have assumed the government of the place, and, being left undisturbed, became a person of some local importance. The boy was put out to nurse, and he used to tell how one day his father, coming to see him, found that the nurse had gone out on pleasure bent, while she had left him suspended by a small cord to a nail fixed in the wall. This, she explained, was a necessary precaution to prevent him from perishing under the teeth of the various animals and animalcula that roamed on the floor. Poisson used to add that his gymnastic efforts carried him incessantly from one side to the other, and it was thus in his tenderest infancy that he commenced those studies on the pendulum that were there to occupy so large a part of his mature age. He was educated by his father, and destined much against his will to be a doctor. His uncle offered to teach him the art, and began by making him prick the veins of cabbage leaves with a lancet. When perfect in this, he was allowed to put on blisters, but in almost the first case he did this by himself. The patient died in a few hours, and though all the medical practitioners of the place assured him that the event was a very common one, he vowed he would have nothing more to do with the profession. Returning home, he found amongst the official papers sent to his father a copy of the questions set at the Polytechnic school, and at once found his career. At the age of 17 he entered the Polytechnic, and his abilities excited the interest of Lagrange and Laplace, whose friendship he retained to the end of their lives. A memoir on finite differences, which he wrote when only 18, was reported on so favourably by Legendre that it was ordered to be published in the Recueil des Savants Étrangers. Directly he had finished the course, he was made a lecturer at the school, and he continued through his life to hold various government scientific posts and professorships. He was somewhat of a socialist, and remained a rigid republican till 1815, with a view to making another empire impossible. He joined the Legitimists. He took, however, no active part in politics, and made the study of mathematics his amusement as well as his business. His works and memoirs are between 300 and 400 in number. The chief treatises which he wrote were his Traité de mécanique, 2 volumes, 1811 and 1833, which was long a standard work; his Théorie nouvelle de l'action capillaire in 1831, his Théorie mathématique de la chaleur in 1835, to which a supplement was added in 1837, and his Recherches sur la probabilité des jugements in 1837. He had intended, if he had lived, to write a work which should cover all mathematical physics, and in which these would have been incorporated. Of his memoirs on the subject of pure mathematics, the most important are those on definite integrals and the Fourier's series. These are to be found on the Journal Polytechnique from 1813 to 1823, and in the Mémoires de l'Académie for 1823. Their application to physical problems constituting one of his chief claims to distinction, his essay on the calculus of variations, Mémoires de l'Académie, 1833, and his papers on the probability of the mean results of observations, Connaissance des temps, 1827, and following years. Most of his memoirs were published in the 3 periodicals here mentioned. Perhaps the most remarkable of his memoirs on applied mathematics are those on the theory of electrostatics and magnetism, which originated a new branch of mathematical physics. He supposed that the results were due to the attractions and repulsions of imponderable particles. The most important of those on physical astronomy are the 2 read in 1806, printed in 1809, on the secular inequalities of the mean motions of the planets. and on the variations of arbitrary constants introduced into the solutions of questions on mechanics. In those, Poisson discusses the question of the stability of the planetary orbits, which Legendre had already proved to the first degree of approximation for the distributing forces, and shews that the result can be extended to the third order of small quantities. These were the memoirs which led to Lagrange's famous memoir of 1808. Poisson also published a paper in 1821 on the libration of the moon, and another in 1827 on the motion of the earth about its centre of gravity. His most important memoirs on the theory of attraction are one in 1829 on the attraction of spheroids, and another in 1835 on the attraction of a homogeneous ellipsoid. The substitution of the correct equation involving the potential, namely grad squared v equals negative 4 pi rho, for Laplace's form of it, pi squared v equals 0, was first published in 1813 in the Bulletin des Sciences of the Société Philomatique. Lastly, I may mention his memoir in 1825 on the theory of waves. Ampère. André-Marie Ampère was born at Lyon in January 22, 1775, and died at Marseille on June 10, 1836. He was widely read in all branches of learning, and lectured and wrote on many of them, but after the year 1809, when he was made professor of analysis at the Polytechnic School in Paris, he confined himself almost entirely to mathematics and science. His papers on the connection between electricity and magnetism were written in 1820. According to his theory, propounded in 1826, a molecule of matter which can be magnetized is traversed by a cloud of electric current, and a magnetization is produced by any cause which makes the direction of these currents in the different molecules of the body approach parallelism. Fresnel. Augustin Jean Fresnel, born at Broglie on May 10, 1788, and died at Ville d'Avray on July 14, 1827, was a civil engineer by profession, but he devoted his leisure to the study of physical optics. The undulatory theory of light, which Hooke, Huygens, and Euler had supported on a priori grounds, had been based on experiment by the researches of Young. Fresnel deduced the mathematical consequences of these experiments, and explained the phenomenon of the interference of both ordinary and polarized light. Biot. Fresnel's friend and contemporary Jean-Baptiste Biot, who was born at Paris on April 21, 1774, and died there in 1862, requires a word or two in passing. Most of his mathematical work was in connection with the subject of optics, and especially with the polarization of light. His systematic works were produced within the years 1805 and 1817. A selection of his more valuable memoirs was published in Paris in 1858. Arago. François Jean Dominique Arago was born at Estangel in the Pyrenees on February 26, 1786, and died in Paris on October 2, 1853. He was educated at the Polytechnic School, Paris, and we gather from his autobiography that however distinguished were the professors of that institution, they were remarkably incapable of imparting their knowledge or maintaining discipline. In 1804 he was made secretary to the observatory, and then from 1806 to 1809 he was engaged in measuring a meridian arc in order to determine the exact length of a meter. He was then made one of the astronomers at Paris, given a residence there, and made a professor at the Polytechnic School, where he enjoyed a marked success as a lecturer. He subsequently gave popular lectures on astronomy, which were both lucid and accurate, a combination of qualities which was rarer then than now. He reorganized the National Observatory, the management of which had long been inefficient, but in doing this he shewed himself dictatorial and passionate, and the same defects of character revealed themselves in many of the events of his life. He remained to the end a consistent republican, and after the coup d'etat of 1852, though half blind and dying
he resigned his post as an astronomer rather than take the oath of allegiance. It is to the credit of Napoleon III that he gave directions that the old man should be in no way disturbed, and that he should be left free to say and do what he liked. His earliest physical researches were on the pressure of steam at different temperatures and the velocity of sound (1818 to 1822). His magnetic observations mostly took place from 1823 to 1826. He discovered what had been called rotary magnetism, and the fact that most bodies could be magnetized. These discoveries were completed and explained by Faraday. He warmly supported Fresnel's optical theories, and the two philosophers conducted together those experiments on the polarization of light which led to the inference that the vibrations of the luminiferous ether were transverse to the direction of motion, and that the polarization consisted in a resolution of rectilinear motion into components at right angles to each other. The subsequent invention of the polariscope and the discovery of rotatory polarization are due to Arago. The general idea of the experimental determination of the velocity of light in the manner subsequently effected by Fizeau and Foucault was suggested by him in 1838, but his failing eyesight prevented his arranging the details or making the experiments. It will be noticed that some of the last members of the French school were alive at a comparatively recent date, but nearly all mathematical work was done before the year 1830. They are the direct successors of the French writers who flourished at the commencement of this century, and seem to have been out of touch with the great German mathematicians of the early part of it, on whose researches much of the best work of this century is based. They are thus placed here, though their writings are in some cases of a later date than those of Gauss, Abel, Jacobi, and other mathematicians of recent times. The introduction of analysis into England. The complete isolation of the English school and its devotion to geometrical methods are the most marked features in its history during the latter half of the 18th century, and the absence of any considerable and valuable contributions to the advancement of mathematical science was a natural consequence. One result of this was that the energy of the English men of science was largely devoted to practical physics and practical astronomy, which were in consequence studied in Britain perhaps more than elsewhere. Almost the only English mathematician at the beginning of this century who used analytical methods and whose work requires mention here is Ivory, to whom the celebrated theorem of attractions is due. James Ivory was born in Dundee in 1765 and died at Douglastown on September 21, 1845. After graduating at St Andrews, he became the managing partner in a flax spinning company in Forfarshire, but continued to devote most of his leisure to mathematics. In 1804 he was made professor at the Royal Military College at Marlow, which is now moved to Sandhurst. He contributed numerous papers to the Philosophical Transactions, the most remarkable being those on attractions. In one of these, in 1809, he shewed how the attraction of a homogeneous ellipsoid on an external point is a multiple of that of another ellipsoid on an internal point. The latter can be easily obtained. He criticized Laplace's solution of the method of least squares with unnecessary bitterness, and in terms which proved his incompetence to understand it. The Cambridge Analytical School. Toward the close of the last century, the more thoughtful members of the Cambridge School of Mathematics began to recognize that their isolation from the continental contemporaries was a serious evil. The earliest attempt in England to explain the notation and methods of the calculus as used on the continent was due to Woodhouse, who stands out as the apostle of the new movement. It is doubtful if he could have brought the analytical methods into vogue by himself, but his views were enthusiastically adopted by three undergraduates, Babbage, Peacock, and Herschel, who succeeded in carrying out reforms that he had suggested. In a book which will fall into the hands of few but English readers, I may be pardoned for making space for a few remarks on these four mathematicians. The original stimulus came from French sources, and I therefore place these remarks at the close of my account of the French school. But I should add that the English mathematicians of this century at once struck out a line independent of their French contemporaries. Woodhouse. Robert Woodhouse was born at Norwich on April 28, 1773, was educated at Caius College, Cambridge, of which society he was subsequently a fellow, was Plumian professor in the university, and continued to live at Cambridge till his death on December 23, 1827. His earliest work, entitled The Principles of Analytical Calculation, was published at Cambridge in 1803. In this he explained the differential notation and strongly pressed the employment of it, but he severely criticized the methods used by continental writers and their constant assumption of non-evident principles. This was followed in 1809 by a trigonometry, plane and spherical, and in 1810 by a historical treatise on the calculus of variations and isoperimetrical problems. He next produced an astronomy, the first volume, usually bound in two, on practical and descriptive astronomy, being issued in 1812, the second volume containing an account of the treatment of physical astronomy by Laplace and other continental writers, being issued in 1818. All these works deal critically with the scientific foundation of the subjects considered, a point which is not unfrequently neglected in modern textbooks. A man like Woodhouse, of scrupulous honour, universally respected, a trained logician, and with a caustic wit, was well fitted to introduce a new system, and the fact that when he first called attention to the continental analysis he exposed the unsoundness of some of the usual methods of establishing it more like an opponent than a partisan, and was politic as it was honest. Woodhouse did not exercise much influence on the majority of his contemporaries, and the movement might have died away for the time being had it not been for the advocacy of Peacock, Herschel, and Babbage, who formed an analytical society with the object of advocating the general use in the university of analytical methods and of the differential notation. Peacock. George Peacock, who was the most influential of the early members of the new school, was born at Denton on April 9, 1791. He was educated at Trinity College, Cambridge, of which society he was subsequently a fellow and tutor. The establishment of the University Observatory was mainly due to his efforts, and in 1836 he was appointed to the Lowndean professorship of astronomy and geometry. In 1839 he was made Dean of Ely, and resided there until his death on November 8, 1858. Although Peacock's influence on English mathematicians was considerable, he has left but few memorials to his work. But I may note that his report on recent progress in analysis 1833 commenced those valuable summaries of scientific progress which enrich many of the annual volumes of the Transactions of the British Association. Babbage. Another important member of the Analytical Society was Charles Babbage, who was born at Totnes in December 26, 1792. He entered Trinity College, Cambridge in 1810, subsequently became Lucasian professor in the university, and died in London on October 18, 1871. It was he who gave the name to the Analytical Society, which he stated was formed to advocate the principles of pure deism as opposed to the dotage of the university. In 1820 the Astronomical Society was founded mainly through his efforts, and at a later time, 1830 to 1832, he took a prominent part in the foundation of the British Association. He will be remembered for his mathematical memoirs on the calculus of functions, and in the invention of analytical machines, which could not only perform ordinary processes of arithmetic, but could tabulate the values of any functions and print the results. Herschel. The third of those who helped bring analytical methods into general use in England was the son of Sir William Herschel, 1738 to 1822, the most illustrious astronomer of the latter half of the last century, and the creator, it may be fairly said, of stellar astronomy. Sir John Frederick William Herschel was born on March 7, 1792, and educated at St. John's College, Cambridge, and died on May 11, 1871. His earliest original work was a paper on Coates's theorem, and it was followed by others on mathematical analysis, but his desire to complete his father's work led ultimately to his taking up astronomy. His papers on light and astronomy contain a clear exposition of the principles which underlie the mathematical treatment of those subjects. In 1813 the Analytical Society published a volume of memoirs, of which the preface and the first paper on continued products are due to Babbage, and 3 years later they issued a translation of Lacroix' Traité des élémentaires du calcul différentiel et du calcul intégral. In 1817 and again in 1819 the differential notation was used in the university examinations, and after 1820 its use was well established. The Analytical Society followed up this rapid victory by the issue in 1820 of 2 volumes of examples illustrative of the new method, one by Peacock on the differential and integral calculus, and the other by Herschel on the calculus of finite differences. Since then, English works on the infinitesimal calculus have abandoned the exclusive use of the fluxional notation. It should be noticed in passing that Lagrange and Laplace, like the majority of other modern writers, employ both the fluxional and the differential notation. It was the exclusive adoption of the former that was so hampering. Amongst those who materially assisted in extending the use of the new analysis were William Whewell (1794 to 1866) and George Bedell Airy (1801 to 1892), both fellows at Trinity College, Cambridge. The former issued in 1819 a work on mechanics, and the latter, who was a pupil of Peacock, published in 1826 in his tracts, in which the new method was applied with great success to various physical problems. The efforts of the Society were supplemented by the rapid publication of good textbooks in which analysis was freely used. The employment of analytical methods spread from Cambridge over the rest of Britain, and by 1830 those methods have come into general use there. End of section 32. Chapter 19. Mathematicians of recent times. It is evidently impossible for me to discuss adequately the mathematicians of the age in which we live, especially as I purposely exclude from this work and any detailed reference to living writers. I make therefore no attempt to give a complete history of this period, but as a sort of appendix to the preceding chapters I add a few notes on some of the more striking features in the history during this century of pure mathematics, in which I include theoretical dynamics and astronomy. But except for a few allusions I shall not discuss the applications of mathematics to physics. These notes are brief, and in many cases consist merely of a list of the names of some of those to whom the development of any branch of the subject is chiefly due, and an indication of that part of it to which they have directed most attention. I would refer anyone who wishes for more details to the invaluable catalogue which has been compiled by the Royal Society of London, and which contains a list under the names of the authors of all the scientific papers contributed during this century to journals and learned societies. In only a few cases do I add any account of the life and works of the mathematicians mentioned. Even with these limitations it has been very difficult to put together a connected account of the mathematicians of recent times, and I wish to repeat explicitly that I do not suggest, nor do I wish my readers to suppose, that my notes on a subject give the names of all the chief writers who have studied it. In fact, the quantity of matter produced has been so enormous that no one can expect to do more than make himself acquainted with the work in some small department. As an illustration of this remark, I must say that I have reason to believe that something like 15,000 separate scientific memoirs are now published every year by the different societies and journals of Europe and America. Most of the treatises on the history of mathematics omit all references to the work produced during this century. The chief exceptions which I am acquainted are a short dissertation by H. Hankel entitled Die Entwicklung der Mathematik in den letzten Jahrhunderten in Tübingen, 1885, the 11th and 12th volumes of Marie's Histoire des Sciences, in which there are notes on mathematicians who were born in the last century, Gerhardt's Geschichte der Mathematik in Deutschland, published in Munich, 1877, and a discours on the professors at the Sorbonne by Hermite in the Bulletin des Sciences Mathématiques in 1890, pages 6 to 36. A few histories of the development of a particular subjects have been written, such as those by the late Isaac Todd Hunter on the theories of attraction and the calculus of probabilities, while annual volumes of the British Association contain a number of reports on the progress in several different branches of modern mathematics. A few similar reports, and notably one in 1857 by J. Bertrand on the development of mathematical analysis, have been presented by the French Academy. I have found these authorities and these reports useful, but I have derived most assistance in writing this chapter from the obituary notices in the proceedings of various learned societies, foreign as well as British. I am also indebted to information kindly furnished me by various friends, and if I do not further dwell on this, it is only that I would not seem to make them responsible for errors and omissions which they would have avoided in their own works. A period of exceptional intellectual activity in any subject is usually followed by one of comparative stagnation, and after the deaths of Lagrange, Laplace, Legendre, and Poisson of the French school, which had occupied so prominent a position at the beginning of this century, ceased for some years to produce much new work. Some of the mathematicians whom I intend first to mention, Gauss, Abel, and Jacobi, were contemporaries of the later years of the French mathematicians just named, but their writings appear to me to belong to a different school, and thus are properly placed at the beginning of a fresh chapter. There is no mathematician of this century whose writings have had a greater effect than those of Gauss, nor is it on only one branch of the science that his influence has left a permanent mark. I cannot therefore commence my account of the mathematicians of recent times better than by describing very briefly his more important researches. Gauss. Carl Friedrich Gauss, born at Brunswick on April 23, 1777, and died in Göttingen on February 23, 1855. His father was a bricklayer, and Gauss was indebted for liberal education, much against the will of his parents, who wished to profit by his wages as a labourer, to the notice which his talents procured from the reigning duke. In 1792 he was sent to the Caroline College, and by 1795 professors and pupils alike admitted that he knew all of the former could teach him. It was while there that he investigated the method of least squares, and proved by induction the law of quadratic reciprocity. Thence he went to Göttingen, where he studied under Kastner. Many of his discoveries in the theory of numbers were made while a student there. In 1798 he returned to Brunswick, where he earned a somewhat precarious livelihood by private tuition. In 1799 Gauss published his demonstration that every algebraical equation has a root of the form a plus bi, a theorem of which altogether he gave three distinct proofs. In 1801 this was followed by Disquisitiones Arithmeticae, which is printed as the first volume of his collected works. The greater part of it has been sent to the French Academy in the preceding year, and has been rejected with a sneer which, even if the book had been as worthless as the referees believed, would have been unjustifiable. Gauss was deeply hurt, and his reluctance to publish his investigations may be partly attributable to this unfortunate incident. The next discovery Gauss was in a totally different department of mathematics. The absence of any planet in the space between Mars and Jupiter, where Bode's law would have led observers to expect one, had been long remarked, but it was not until 1801 that any one of the numerous group of minor planets which occupy that space was observed. The discovery was made by Piazzi of Palermo, and was the more interesting as its announcement occurred simultaneously with a publication by Hegel in which he severely criticized astronomers for not paying more attention to philosophy, a science, said he, which would not at once have shewn them that there could not possibly be more than 7 planets, a study of which would therefore have prevented an absurd waste of time in looking for what in the nature of things could never be found. The new planet was named Ceres, but it was seen under conditions which appeared to render it almost impossible to forecast its orbit. The observations were fortunately communicated to Gauss. He calculated its elements, and his analysis proved to him to be the first of theoretical astronomers no less than the greatest of arithmeticians. The attention excited by these investigations procured him in 1807 the offer of a chair at St. Petersburg, which he declined. In the same year he was appointed director to Göttingen Observatory and professor of astronomy there. These offices he retained to his death, and after his appointment he never slept away from his observatory except on one occasion where he attended a scientific conference at Berlin. His lectures were singularly lucid and perfect in form, and it is said that he used here to give the analysis by which he had arrived at his various results, and which it is so conspicuously absent from his published demonstrations, but for fear his auditors should lose the thread of his discourse, he never willingly permitted them to take notes. I have already mentioned Gauss's publications in 1799, 1801, and 1802. For some years after 1807 his time was almost wholly occupied by work connected with his observatory. In 1809 he published at Hamburg his Theoria Motus Corporum Celestium, a treatise which contributed largely to the improvement of practical astronomy and introduced the principle of curvilinear triangulation; and on the same subject, but connected with observations in general, we have his memoir Theoria Combinatonis Observationum Aerobinus Minimus Obnoxia, with a second part and a supplement. Somewhat later he took up the subjects of geodesy, acting from 1821 to 1848 as scientific adviser to the Danish and Hanoverian governments for the survey then in progress. His papers of 1843 and 1866 Über Gegenstände der hohen Geodäsie contain his researches on the subject. Gauss's researches on electricity and magnetism date from about the year 1830. His first paper on the theory of magnetism, entitled Intensitas vis magnetica terrestris ad mensuram absolutum revocata, was published in 1833. A few months afterwards he, together with Weber, invented the declination instrument and the bifilar magnetometer, in the same year that they erected at Göttingen a magnetic observatory free from iron, as Humboldt and Arago had previously done on a smaller scale, where they made magnetic observations, and in particular shewed that it was possible and predictable to send telegraph signals. In connection with this observatory Gauss founded the association called the Magnetische Verein, with the object of securing continuous observations at fixed times. The volumes of their publications Resultate aus der Beobachtung des magnetischen Vereins for 1838 and 1839 contain two important memoirs by Gauss, one on the general theory of earth magnetism and on the other on the theory of forces attracting according to the inverse square of the distance. Like Poisson, he treated the phenomenon in electrostatics as due to attractions and repulsions between imponderable particles. In electrodynamics he arrived in 1835 at a result equivalent to that given by W. E. Weber in 1846, namely that the attraction between two electrified particles E and E', whose distance apart is r, depends on their relative motion and position according to the formula E r to the power of minus 2 multiplied by the quantity 1 plus r umlaut minus 1 half r squared quantity squared times c to the minus 2. Gauss, however, held that no hypothesis was satisfactory which rested on a formula and was not a consequence of a physical conjecture, and as he could not frame a plausible physical conjecture he abandoned the subject. Such conjectures were proposed by Riemann in 1858 and by C. Neumann and E. Betti in 1868. But Helmholtz in 1870, 1873, and 1874 shewed that they were untenable. A simpler view which regards all electric and magnetic phenomena as stresses and motions of a material elastic medium have been outlined by Michael Faraday and was elaborated by James Clerk Maxwell. The latter, by the use of generalized coordinates, was able to deduce the consequences, and the agreement with experiment is close. These and other electric theories were classified and critically discussed in a memoir by J. Thomson in 1885. Gauss's researches on optics, including systems of lenses, were published in 1840 in his Dioptrische Untersuchungen. From this sketch it will be seen that the ground covered by Gauss's researches was extraordinarily wide. I will now mention very briefly some of his most important discoveries in pure mathematics. His most celebrated work in pure mathematics is De Disquisitiones Arithmeticae, which has proved the starting point for several interesting investigations on the theory of numbers. This treatise and Legendre's Théorie des Nombres remains standard works on the theory of numbers. But, just as in his discussion of elliptic functions, Legendre failed to rise to the conception of a new subject, and confused himself to regarding their theory as a chapter in the integral calculus, so he treated the theory of numbers as a chapter in algebra. Gauss, however, realized that the theory of discrete magnitudes or higher arithmetic was of a different kind from that of continuous magnitudes or algebra, and he introduced a new notation and new methods of analysis, of which subsequent writers have generally availed themselves. In particular, the Disquisitiones Arithmeticae introduced the modern theory of congruences of the first and second orders, and to this Gauss reduced intermediate analysis. In it also he discussed the solution of binomial equations of the form x to the power n equals 1. This involves the celebrated theorem that the only regular polygons which can be constructed by elementary geometry are those in which the number of sides is 2 to the power of m multiplied by 2 to the power of n plus 1, where m and n are integers and 2 to the power n plus 1 is a prime, a discovery he had made in 1796. He developed the theory of ternary quadratic forms involving two indeterminates. He also investigated the theory of determinants, and it was on Gauss's results that Jacobi based his researches on that subject. The theory of functions of double periodicity had its origin in the discoveries of Abel and Jacobi, which I describe later. Both these mathematicians arrived at the theta functions which play so large a part in the theory of the subject. Gauss, however, had independently and indeed at a far earlier date discovered these functions and their chief properties, having been led to them by certain integrals which occurred in the determinatio attractionis, to evaluate which he invented the transformation now associated with the name of Jacobi. Though Gauss at a later time communicated the fact to Jacobi, he did not publish his researches. They occur in a series of notebooks of a date not later than 1808 and are included in his collected works. Of the remaining memoirs in pure mathematics, the most remarkable are those on the theory of biquadratic residues, wherein the notion of complex numbers of the form a plus bi was first introduced into the theory of numbers, in which are included several tables, and notably one of the number of the classes of binary quadratic forms, that of relating to the proof of the theorem that every numerical equation has a real or imaginary root, that on the summation of series, that on the hypergeometric series, which contains a discussion of the gamma function, and lastly one on interpolation. His introduction of rigorous tests for the convergency of infinite series is especially noticeable. Finally, we have the important memoir on the conformal representation of one surface upon another, in which the results given by Lagrange for surfaces of revolution are generalized for any surfaces. In the theory of attractions, we have a paper on the attraction of homogeneous ellipsoids. The already mentioned memoir of 1839, Allgemeine Lesssatz in Beziehung auf die inverkehrten Verhältnis des Quadrats der Entfernung, on the theory of forces attracting according to the inverse square of the distance, and the memoir Determinatio Attractionis, in which it is shewn that the secular variations which the elements of the orbit of a planet experience from the attraction of another planet which disturbs it are the same as if the mass of the disturbing planet were distributed over its orbit into an elliptic ring in such a manner that equal masses of the ring would correspond to the arcs of the orbit described in equal times. The great masters of modern analysis are Lagrange, Laplace, and Gauss, who were contemporaries. It is interesting to note the marked contrast in their styles. Lagrange is perfect both in form and matter. He is careful to explain his procedure, and though his arguments are general, they are easy to follow. Laplace, on the other hand, explains nothing, is absolutely indifferent to style, and if satisfied with that his results are correct, is content to leave them either with no proof or with a faulty one. Gauss is as exact and elegant as Lagrange, but even more difficult to follow than Laplace, for he removes every trace of the analysis by which he reached his results, and studies to give a proof which, while rigorous, shall be as concise and synthetical as possible. End of part 34. Chapter 19. Mathematics of Recent Times, Part 2. Dirichlet. One of Gauss's pupils to whom I may here allude is Lejeune Dirichlet, who is generally known for his exposition of the discoveries of Jacobi, who was his father-in-law, and of Gauss, rather than for his own original investigations, valuable though some of these are. Peter Gustave Lejeune Dirichlet was born at Rennes on February 13, 1805, and died at Göttingen on May 5, 1859. He held successively professorships at Breslau and Berlin, and on Gauss's death in 1855 was appointed to succeed him as professor of the higher mathematics at Göttingen. He intended to finish Gauss's incomplete works, for which he was admirably fitted, but his early death prevented this. He produced, however, several memoirs which have considerably facilitated the comprehension of some of Gauss's more abstruse methods. Of Dirichlet's original work, the most celebrated is that on the determination of means with applications to the distribution of prime numbers. The researches of Gauss on the theory of numbers were continued or supplemented by Jacobi, who first proved the law of cubic reciprocity, discussed on the theory of residues, and in his Canon Arithmeticus gave a table of residues of prime roots. Eisenstein. This subject was next taken up by Ferdinand Gotthold Eisenstein, a professor at the University of Berlin, who was born at Berlin on April 16, 1823, and died there on October 11, 1852. The theory of numbers may be divided into two main divisions, namely the theory of congruences and the theory of forms. The solution of the problem of the representation of numbers by binary quadratic forms is one of the great achievements of Gauss, and the fundamental principles upon which the treatment of such questions rest were given by him in the Disquisition arithmétique. Gauss there added some results relating to ternary quadratic forms, but the general extension from 2 to 3 indeterminates was the work of Eisenstein, who in his memoir Neue Theorem der höheren Arithmetik defined the ordinal and generic characters of ternary quadratic forms of an uneven determinant, and in the case of definite forms assigned the weight of any order or genus, but he did not consider forms of an even determinant, nor give any demonstration of his work. Eisenstein also considered the theorems relating to the possibility of representing a number as a sum of squares, and shewed that the general theorem was limited to 8 squares. The solutions in the cases of 2, 4, and 6 squares may be obtained by means of elliptic functions, but the cases in which the numbers of squares is uneven involve the special processes peculiar to the theory of numbers. Eisenstein gave the solution in the case of 3 squares. He also left a statement of the solution he had obtained in the case of 5 squares, but his results were published without proofs and apply only to numbers which are not divisible by a square. Among Eisenstein's other investigations I single out for special mention the remarkable rule he enunciated by means of which it is possible to distinguish whether a given series represents an algebraical or transcendental function. Henry Smith. One of the most original and powerful mathematicians of the school founded by Gauss was Henry Smith. Henry John Stephen Smith was born in London on November 2, 1826, and died at Oxford on February 9, 1883. He was educated at Rugby and at Balliol College, Oxford, of which latter society he was a fellow, and in 1861 he was elected Savilian Professor of Geometry at Oxford, where he resided till his death. The subject in connection with which Smith's name will be always specially remembered is the theory of numbers, and to this he devoted the years from 1854 to 1864. The results of his historical researches were given in his report published in parts in the Transactions of the British Association from 1859 to 1865. This report contains an account of what had been done on the subject to that time, together with some additional matter. The chief outcome of his own original work on the subjects is included in 2 memoirs printed in the Philosophical Transactions for 1861 and 1867, the first being on linear indeterminate equations and congruences, and the second on the orders and genera of ternary quadratic forms. In the latter memoir, demonstrations of Eisenstein's results and their extension to ternary quadratic forms of an even determinant were supplied, and a complete classification of ternary quadratic forms was given. Smith, however, did not confine himself to the case of 3 indeterminates, but succeeded in establishing the principles on which the extension to the general case of n indeterminates depends, and obtained the general formulae, thus effecting the greatest advance made in the subject since the publication of Gauss's work. In the account of his methods and results which appeared in the Proceedings of the Royal Society, Smith remarked that the theorems relating to the representation of numbers by 4 squares and other simple quadratic forms are deducible by a uniform method from the principles there indicated, as also are the theorems relating to the representation of numbers by 6 and 8 squares. He then proceeded to say that as the series of theorems relating to the representation of numbers by sums of squares ceases, for the reason assigned by Eisenstein, when the number of squares surpasses 8, it was desirable to complete it. The results for even squares were known. The principal theorems relating to the case of 5 squares had been given by Eisenstein, but he had considered only those numbers which are not divisible by a square, and he had not considered the case of 7 squares. Smith here completed the enunciation of the theorems for the case of 5 squares, and added the corresponding theorems for the case of 7 squares. This paper was the occasion of a dramatic incident in the history of mathematics. 14 years later, in ignorance of Smith's work, the demonstration and completion of Eisenstein's theorems for 5 squares were set by the French Academy as a subject of their Grand Prix des Sciences Mathématiques. Smith wrote out the demonstration of his general theorems so far as was required to prove the results in the special case of 5 squares, and only a month after his death in March 1883 the prize was awarded to him, another prize being awarded to H. Minkowski of Bonn. No episode could bring out in a more striking light the extent of Smith's researches than that a question of which he had given in the solution in 1867 as a corollary from the general formulae which governed the whole class of investigations to which it belonged should have been regarded by the French Academy as one whose solution which was of such difficulty and importance as to be worthy of their great prize. It has also been a matter of comment that they should have known so little of contemporary English and German researches on the subject as to be unaware that the result of the problem they were proposing was then lying in their own library. Among Smith's other investigations I may specially mention his geometrical memoir Sur calcul problème cubique et biquadratique, for which in 1868 he was awarded the Steiner Prize of the Berlin Academy. In a paper which he contributed to the Atti of the Academia des Lyncées for 1877 he established a very remarkable analytical relation connecting the modular equation of order n and the theory of binary quadratic forms belonging to the positive determinant n. In this paper the modular curve is represented analytically by a curve in such a manner as to present an actual geometrical image of the complete systems of the reduced quadratic forms belonging to the determinant, and a geometrical interpretation is given to the ideas of class, equivalence, and reduced form. He was also the author of important papers in which he succeeded in extending to complex quadratic forms many of Gauss's investigations relating to real quadratic forms. He was led by researches on the theory of numbers to the theory of elliptic functions, and the results he arrived at, especially on the theory of the theta and omega functions, are of importance. The theory of numbers as treated today may be said to originate with Gauss. I have already mentioned very briefly the subject of the subsequent investigations of Jacobi, Dirichlet, Eisenstein, and Henry Smith. Among other mathematicians who have written on it I may allude to the following: Riemann, who investigated the distribution of primes; James Joseph Sylvester, civilian professor in the University of Oxford, born in London on September 3, 1814, who has also written on the distribution of primes; Cauchy, who in particular discussed the expression of quadratic binomials; Joseph Liouville, the editor from 1836 to 1874 of the well-known journal, who was born at Saint Omer on March 24, 1809, and died in 1882, most of whose numerous investigations dealt with the representation of numbers by special forms; Ernest Edward Kummer, born at Sorau on January 29, 1810, and until recently professor at Berlin, to whom we owe the conception of the so-called ideal primes which are required in the treatment of complexes and which he applied to the problem of Fermat's equation, and whose paper on hypergeometric series may rank with that by Gauss as a classical memoir on the subject. Leopold Kronecker, professor in Berlin, born at Liegnitz on December 7, 1823, and died at Berlin on December 29, 1891, most of whose investigations on this branch of mathematics were on ternary and quadratic forms. On his investigations generally see the Bulletin of the New York Mathematical Society, Volume 1, pages 173 to 184. See also below, page 469. Charles Hermite, professor in Paris, born in Lorraine on December 24, 1822, who wrote on ternary forms. Julius Wilhelm Richard Dedekind, born at Brunswick on October 6, 1831, whose more important researches given in an appendix to his edition of Dirichlet's writings are on ideal primes. See also below, page 493. Panutij Chebyshev, formerly professor at the University of St. Petersburg, born in Russia in 1821, who has written on the number of primes between given limits, a problem also considered by Legendre, Dirichlet, and Riemann. And James Whitebread Lee Glaisher, a fellow and tutor of Trinity College in Cambridge, born at Lewisham on November 5, 1848, from whose numerous papers I may single out those relating to prime numbers, those on functions of a number which are formed from its real or complex divisors, and on those on the possible divisors of numbers of a given form. Finally, I may mention that the problem of the partition of numbers, to which Euler paid considerable attention, has in recent times attracted the attention of Arthur Cayley, Sadlerian professor in the University of Cambridge, born in Richmond, Surrey, on August 16, 1821, of Sylvester, and of Percy Alexander MacMahon, professor at Woolwich and a major in the English artillery, born at Malta on September 26, 1854. Interest in problems connected with the theory of numbers seems recently to have flagged, and possibly it may be found hereafter that the subject is approached better on other lines. The theory of functions of double and multiple periodicity is another subject to which much attention has been paid during this century. I have already mentioned that as early as 1808 Gauss had discovered the theta functions and their chief properties, but his investigations remained for many years concealed in notebooks, and it was to the researches made between 1820 and 1830 by Abel and Jacobi that the modern development of the subject is due. The treatment of it has been completely superseded that used by Legendre, and they are justly reckoned as the creators of this branch of mathematics. Abel. Niels Henrik Abel, born at Findo in Norway on August 5, 1802, and died at Arendal on April 6, 1829, at the age of 26. His memoirs on elliptic functions, which were originally published in Krell's journal, treat the subject from the point of view of the theory of equations and algebraic forms, a treatment to which his researches naturally led him. The important and very general result known as Abel's theorem, which was subsequently applied by Riemann to the theory of transcendental functions, was sent to the French Academy in 1828, but, mainly through the action of Cauchy, was not published for several years. The name of Abelian function has been given to the higher transcendents of multiple periodicity, which were first discussed by Abel. He criticized the use of infinite series, but I do not know that the results lead to any definite rules for testing convergency. As illustrating his fertility of ideas, I may in passing notice his celebrated demonstration that it is impossible to solve a quintic equation by means of radicals. This theorem was the more important since it definitely limited a field of mathematics which had previously attracted numerous writers. I should add that this theorem had been enunciated as early as 1798 by Paolo Ruffini, an Italian physician practicing at Modena, but I believe that the proof he gave was deficient in generality. Jacobi. Carl Gustav Jacob Jacobi, born of Jewish parents at Potsdam on December 10, 1804, and died at Berlin on February 18, 1851, was educated at the University of Berlin, where he obtained the degree of Doctor of Philosophy in 1825. In 1827 he became extraordinary professor of mathematics at Königsberg, and in 1829 was promoted to be an ordinary professor. This chair he occupied till 1842, when the Prussian government gave him a pension, and he moved to Berlin, where he continued to live until his death in 1851. Jacobi's most celebrated investigations are those on elliptic functions, the modern notation in which is due to him, and the theory of which he established simultaneously with Abel but independently of him. These are given in his treatise Fundamenta Nova Theoreae Functionum Ellipticarum, Königsberg, 1829, and in some later papers in Crell's journal. The correspondence between Legendre and Jacobi on elliptic functions has been reprinted in the first volume of Jacobi's collected works. Jacobi, like Abel, recognized that elliptic functions were not merely a group of theorems on integration, but that they were types of a new kind of function, namely one of double periodicity. Hence he paid particular attention to the theory of the theta function. The following passage in which he explains this view is sufficiently interesting to deserve textual reproduction. Equo cum universam que fingipotest amplicatur periodaticatam analyticam elucit functiones ellipticas non alis ad numerari deber transcendentibus que quibusdem godent elegantis fortas pluribus illas aut melioribus, sed speciem quadnam is ines perfecti et absoluti. Among Jacobi's other investigations I may specially single out his papers on determinants, which did a great deal to bring them into general use, and particularly his invention of the Jacobian, that is, of the functional determinant formed by the n squared partial differential coefficients of the first order of n, given functions of n independent variables. I ought also to mention his papers on Abelian transcendents, his investigations on the theory of numbers, his important work on the theory of partial differential equations, his development of the calculus of variations, and his numerous memoirs on the planetary theory and other particular dynamical problems, in the course of which he also extended the theory of differential equations. Most of the results of the researches last named are included in his Vorlesungen über Dynamik, edited by Klebsch, Berlin, 1866. Riemann. Georg Friedrich Bernhard Riemann was born at Bersens on September 17, 1826, and died at Selaska on July 20, 1866. He studied at Göttingen under Gauss, and subsequently at Berlin under Jacobi, Dirichlet, Steiner, and Eisenstein, all of whom were professors there at the same time. His earliest paper, written in 1850, was on algebraic functions of a complex variable, and on it the recent investigations of Schwarz, Klein, and Poincaré are largely based. To those I refer very briefly below. In 1854 Riemann wrote his celebrated memoir on the hypotheses on which geometry is founded. This was succeeded by his memoirs on elliptic functions and the theory of numbers. He also wrote on physical subjects. The question of the truth of the assumptions usually made in our geometry had been considered by J. Sacheri as long ago as 1733, and in more recent times had been discussed by Nikolai Ivanovich Lobachevsky, professor at Caen, born at Nizhny Novgorod in 1793 and died at Kazan on February 12, 1856, in 1826 and again in 1840. By Gauss in 1831 and in 1846, and by Johann Bolyai, born at Klausenburg in 1802 and died at Maros Vasarhelyi in 1860 and in 1832 in the appendix to the first volume of his father's Tentamen, but Riemann's memoir of 1854 attracted general attention to the subject of hypergeometry, and the theory has been since extended and simplified by various writers, notably by Eugenio Beltrami, professor at Pavia, born at Cremona in 1835, and by Hermann Ludwig Ferdinand von Helmholtz, professor at Berlin, born at Potsdam on August 31, 1821. The subject is so technical that I confine myself to a bare sketch of the argument from which the idea is derived. That a space of two dimensions should have the geometrical properties with which we are made familiar in the study of elementary geometry, it is necessary that it should be possible at any place to construct a figure congruent to a given figure, and this is so only if the product of the principal radii of curvature at every point in space or surface be a constant. There are three species of surfaces which possess this property, namely 1. Spherical surfaces where the product is positive, 2. Plane surfaces which led to Euclidean geometry where it is 0, and 3. What Beltrami has called pseudospherical surfaces where it is negative. Moreover, if any surface be bent without dilation or contraction, the measure of curvature remains unaltered. Thus these three species of surfaces are types of three kinds on which congruent figures can be constructed. For instance, a plane can be rolled into a cone, and the system of geometry on a conical surface is similar to that on a plane. These kinds of space of two dimensions are distinguished from one another by a simple test. Through a point of spherical space, no geodetic line, a geodetic line being defined as the shortest distance between 2 points, can be drawn parallel to a given geodetic line. Through a point of Euclidean or plane space, one and only one geodetic line, i.e. a straight line, can be drawn parallel to a given geodetic line. Through a point of pseudospherical space, more than one geodetic line can be drawn parallel to a given geodetic line, but all these lines form a pencil whose vertical angle is constant. It may be thought that we have a demonstration that our space is plane, since through a given point we can draw only one straight line parallel to a given straight line. This is not so, for it is conceivable that our means of observation do not permit us to say with absolute accuracy whether two lines are parallel. Hence we cannot use this as a means to tell whether our space is plane or not. A better test can be deduced from the proposition that in any two-dimensional space of uniform curvature, the sum of the angles of a triangle, if it differ from two right angles, will differ by a quantity proportional to the area of the triangle. Hence it may happen possibly that although for triangles such as we can measure, the difference is imperceptible, yet for triangles which are millions of times bigger there would be a sensible difference. If space be spherical or pseudospherical, its extent is finite. If it be plane, its extent is infinite. In regard to pseudospherical space, I should add that its extent may be infinite if it be constructed in space of 4 dimensions. In the preceding sketch of the foundations of non-Euclidean geometry, I have assumed tacitly that the measure of a distance remains the same everywhere. Klein has shewn that if this be not the case, and if the law of the measurement of distance be properly chosen, we can obtain 3 systems of plane geometry analogous to the 3 systems mentioned above. These are called respectively elliptic, parabolic, and hyperbolic geometries. The above refers only to hyperspace of 2 dimensions. Naturally, there arises the question whether there are different kinds of hyperspace of 3 or more dimensions. Riemann shewed that there are 3 kinds of hyperspace of 3 dimensions having properties analogous to the 3 kinds of hyperspace of 2 dimensions already discussed. These are differentiated by the test whether at every point no geodetical surfaces or one geodetical surface or a fasciculus of geodetical surfaces can be drawn parallel to a given surface, a geodetical surface being defined as such that every geodetic line joining 2 points on it lies wholly on the surface. I return now to Riemann's other investigations. In multiply periodic functions it is hardly too much to say that he in his memoir in Bouchart's journal for 1857 did for the abelian functions what Abel had done for the elliptic functions, and it is this perhaps that will constitute one of his chief claims to future distinction. In the theory of numbers, Riemann's short tract of 8 pages on the number of primes which lie between two given numbers affords a striking instance of his analytical powers. Legendre had previously shewn that the number of primes less than n is very approximately n divided by the quantity log n minus 1.08366. But Riemann went further, and this tract and a memoir by Chebyshev contains nearly all that had been done, yet in connection with a problem of so obvious of a character that it has suggested itself to all who has considered the theory of numbers, and yet which overtaxed the powers even of Lagrange and Gauss. Among others than those already named, I may mention the following who have written on elliptic and abelian functions. Johann Georg Rosenhain, professor in Königsberg, born there on June 10, 1816, and died in 1887, who wrote in 1884 on the hyperelliptic double theta function and functions of two variables with 4 periods. Adolf Goepel, born at Rostock in September 1812 and died at Berlin in March 1847, who discussed hyperelliptic functions. See Krell's Journal, volume 35, 1847, pages 313 to 318. Karl Weierstrass, professor in Berlin, born at Ostenfeld on October 31, 1815, whose earlier researches related to the theta functions which he treated under a modified form in which they are expressible in powers of the modulus. At a later period he developed a method for treating all elliptic functions in a symmetrical manner, a process to which he was naturally led by his researches on the general theory of functions. In this theory, the theta functions are independent of the form of their space boundaries. Leopold Kronecker, who wrote on elliptic functions. Francesco Brioschi of Rome, who wrote on elliptic and hyperelliptic functions. Henry Smith, who discussed the transformation theory, the theta and omega functions, and certain functions of the modulus. Cayley, who was the first to work out in 1845 the theory of doubly infinite products and determine their periodicity, and who has written at length on the connection between the researches of Legendre and Jacobi. His later writings have dealt mainly with the theory of transformations and the modular equation. Cayley's collected works are now being issued by the University of Cambridge. The researches of Hermite are mostly concerned with the transformation theory, the higher development of the theta functions, and the connection between the methods and results of Weierstrass and Jacobi. The transformation of the double theta function has been also considered by Leo Königsberger, professor at Heidelberg, born in Prussia 1837. See his lectures published at Leipzig in 1874. The investigations of George Henri Haffan, an officer in the French army, born at Rouen on October 30, 1844, and died in Paris on May 21, 1889, are largely founded on Weierstrass's work. A sketch of Halphen's life and works given in Liouville's journal for 1889, pages 345 to 359, and in the Comptes Rendus, 1890, volume 110, pages 489 to 497. See also below, pages 481 to 482. Felix Christian Klein, born in 1849, now professor in Göttingen, has written on abelian functions, elliptic, modular functions, and hyperelliptic functions. Finally, H. A. Schwarz, formerly of Göttingen, now in Berlin, born 1845. H. W. Weber of Marburg, M. Nother of Erlangen, W. Stahl of Aix-la-Chapelle, F. G. Frobenius, now of Berlin and formerly of Zurich, and Glaisher have written on various branches of the theory, and Dr. Glaisher has in particular developed the theory of the zeta function. The textbook by Briot and Bouquet contains a clear account of the elliptic functions as it exists at present, developed from the point of view of the complex variable. Albert Briot was born at Saint Hippolyte in 1817, occupied a chair at the Sorbonne in Paris, and died in 1882. Jean-Claude Bouquet was born in 1819 and died in Paris in 1885. End of section 35. Chapter 19. Mathematics of Recent Times, Part 3. The consideration of algebraical, trigonometrical, elliptic, hyperelliptic, and other special kinds of functions paved the way for a theory of functions, which promises to prove a most important and far-reaching branch of mathematics. To a large extent, this is the work of living mathematicians, and therefore outside the limits of this chapter. I will content myself by referring to the following writers. First, I may mention Cauchy, who gave the general elementary theory of functions, and Liouville, who wrote chiefly on doubly periodic functions. Their investigations were extended and connected in the work of Briot and Bouquet, and further been developed by Hermite. Next, I may refer to the researches on the theory of algebraic functions which have their origin in Riemann's paper of 1850. Schwarz has established accurately certain theorems of which proofs given by Riemann were open to objection. Klein has connected Riemann's theory of functions with the theory of groups and have written on automorphic functions. Henri Poincaré, professor in Paris, born at Nancy in 1854, has also written on automorphic functions and on the general theory with special applications to differential equations. Finally, I may refer to the work of Weierstrass and Mittag-Leffler. Of these, Karl Weierstrass has created a large part of the modern theory of functions, and in particular has constructed the theory of uniform analytical functions. And Magnus Gustav Mittag-Leffler, born at Stockholm in 1846 and now professor there, has greatly developed the theory of analytical functions, a subject on which Hermite has also written. In connection with these researches, Paul-Émile Appel, professor in Paris, born at Strasbourg in 1858, C. Émile Picard of Paris, Edouard Goursat of Paris has written on special branches of the theory. As textbooks, I may mention Dr. Forsyth's Theory of Functions of a Complex Variable, Cambridge, 1893, and Karl Neumann's Vorlesungen über Riemanns Theorie der Absälchen Integral, 2nd edition, Leipzig, 1884. The theory of numbers may be considered as a higher arithmetic, and the theory of elliptical and abelian functions as a higher trigonometry. The theory of higher algebra, including the theory of equations, has also attracted considerable attention, and was a favourite subject of study of the three mathematicians, Cauchy, Hamilton, and De Morgan, whom I propose to mention next, though the interests of these writers were by no means limited to this subject. Cauchy. The first of these mathematicians is the best representative of the French school of analysis in this century. Augustin Louis Cauchy, who was born in Paris on August 21, 1789, and died at Sceaux on May 25, 1857, was educated at the Polytechnic School, the nursery of so many French mathematicians of that time, and adopted the profession of a civil engineer. His earliest mathematical paper was one on polyhedra in 1811. Legendre thought so highly of it that he asked Cauchy to attempt the solution of an analogous problem which had baffled previous investigators, and his advice was justified by the success of Cauchy in 1812. Memoirs on analysis and the theory of numbers presented in 1813, 1814, and 1815 shewed that his ability was not confined to geometry alone. In one of these papers he generalized some results which had been established by Gauss and Legendre. In another of them he gave a theorem on the number of values which an algebraical function can assume when the literal constants it contains are interchanged. It was the latter theorem that enabled Abel to shew that in general an algebraic equation of a degree higher than the fourth cannot be solved by the use of purely algebraical expressions. To Cauchy and Gauss we owe the scientific treatment of series which have an infinite number of terms, and the former established general rules for investigating the convergency and divergency of such series. It is only a few works of an earlier date that contain any discussion as to the limitations of the series employed. It is said that Laplace, who was present when Cauchy read his first paper on the subject, was so impressed by the illustrations of the danger of employing such series without a rigorous investigation of their convergency that he put on one side the work on which he was then engaged and denied himself to all visitors, in order to see if any of the demonstrations given in the earlier volumes of the Mécanique Céleste were invalid. And he was fortunate enough to find that no material errors had been thus introduced. The treatment of series and of the fundamental conceptions of the calculus in most of the textbooks then current was based on Euler's works, and to any one trained to accurate habits of thought was not free from objection. It is one of the chief merits of Cauchy that he placed those subjects on a logical foundation. On the Restoration in 1816 the French Academy was purged, and, in spite of the indignation and scorn of French scientific society, Cauchy accepted a seat which was procured for him by the expulsion of Monge. He was also at the same time made professor at the Polytechnic, and his lectures there on algebraic analysis, the calculus, and the theory of curves were published as textbooks. On the Revolution in 1830 he went into exile and was first appointed professor at Turin, where he soon moved to Prague to undertake the education of the Comte de Chambord. He returned to France in 1837 and in 1848 and again in 1851 by special dispensation of the emperor was allowed to occupy a chair of mathematics without taking the oath of allegiance. His activity was prodigious, and from 1830 to 1859 he published in the Transactions of the Academy of the Comtes Rendus over 600 original memoirs and about 150 reports. In most of them the feverish haste with which they were thrown off is too visible, and many are marred by obscurity, repetition of old results, and blunders. Among the more important of his researches are the discussion of tests for the convergency of series, and the determination of the number of real and imaginary roots of any algebraic equation. His method of calculating these roots approximately, his theory of the symmetric functions of the coefficients of equations of any degree, his a priori evaluation of quantity less than the least difference between the roots of an equation, and his papers on determinants in 1841, which did a great deal to bring them into general use. Cauchy also did something to reduce the art of determining definite integrals to a science, but this branch of the integral calculus still remains without much system or method. The rule for finding the principal values of integrals was enunciated by him, and the calculus of residues was his invention. His proof of Taylor's theorem seems to have originated from a discussion of the double periodicity of elliptic functions. The means of shewing a connection between the different branches of a subject by giving imaginary values to independent variables is largely due to him. He also gives a direct analytical method for determining planetary inequalities of long period, and to physics he contributed a memoir on the quantity of light reflected from the surfaces of metals, as well as other papers on optics. Argand. I may mention here the name of Jean Robert Argand, who was born at Geneva on July 22, 1768, and died circa 1825. In his essay, issued in 1806, he gave a geometrical representation of a complex number, and applied it to shew that every algebraic equation has a root. This was prior to the memoirs of Gauss and Cauchy on the same subject. But the essay did not attract much attention when it was first published. An earlier demonstration that the square root of -1 indicates perpendicularity due to Buet was published in the Philosophical Transactions for 1806, and the idea was foreshadowed in a memoir by H. Kuhn in the Transactions for 1750 of the St. Petersburg Academy. Hamilton. In the opinion of some writers, the theory of quaternions will be ultimately esteemed by one of the great discoveries of this century. The discovery is due to Sir William Rowan Hamilton, who was born of Scotch parents in Dublin on August 4, 1805, and died there on September 2, 1865. His education, which was carried out at home, seems to have been singularly discursive. Under the influence of an uncle who was a good linguist, he first devoted himself to linguistic studies. By the time he was 7 he could read Latin, Greek, French, and German with facility, and when 13 he was able to boast that he was familiar with as many languages as he had lived years. It was about this time that he came across a copy of Newton's Universal Arithmetic. This was his introduction to modern analysis, and he soon mastered the elements of analytical geometry and the calculus. He next read the Principia and the 4 volumes then published of Laplace's Mécanique Céleste. In the latter he detected a mistake, and his paper on the subject, written in 1823, placed him at once in the front rank of mathematicians. In the following year he entered at Trinity College, Dublin. His university career is unique, for the chair of astronomy becoming vacant in 1827, while he was yet an undergraduate, he was asked by the electors to stand for it, and was elected unanimously, it being understood that he should be left free to pursue his own line of study. His earliest paper, written in 1823, was on optics, and was published in 1828 under the title of A Theory of Systems of Rays, which 2 supplements, written in 1831 and 1832, were afterwards added. In the latter of these the phenomenon of conical refraction is predicted. This was followed by a paper in 1827 on the principle of varying action, and in 1834 and 1835 by memoirs on a general method in dynamics, the subject of theoretical dynamics being properly treated as a branch of pure mathematics. His lectures on quaternions was published in 1852. Amongst his other papers I may specially mention one on the form of the solution of the general algebraic equation of the 5th degree, which confirmed the conclusion arrived at by Abel that it cannot be expressed in terms of the more elementary operations and functions. One on fluctuating functions, one on the hodograph, and lastly on the numerical solution of differential equations. His Elements of Quaternions were issued in 1866. Of this a competent authority says that the methods of analysis there given shew as great an advance over those of analytical geometry as the latter shewed over those of Euclidean geometry. In more recent times the subject has been further developed by Tate. Hamilton was painfully fastidious on what he published, and he left an immense collection of manuscript books which are now in the library of Trinity College, Dublin, and some of which it is hoped will be ultimately printed. Grassmann. The idea of non-commutative algebras and of quaternions seemed to have occurred to Grassmann about the same time as to Hamilton. Hermann Gunther Grassmann, born at Stettin on April 15, 1809, and died there in 1877. He was a professor at the gymnasium at Stettin. His researches on non-commutative algebras are contained in his Ausdehnungslehre, first published in 1844 and enlarged in 1862. The scientific treatment of the fundamental principles of algebra initiated by Hamilton and Grassmann were continued by De Morgan and Boole, and subsequently was further developed by H. Hankel in his work on complexes 1867, and by G. Cantor on his memoirs on the theory of irrationals 1871. The discussion is however so technical that I am unable to do more than allude to it. Grassmann also investigated the properties of homoloidal hyperspace. De Morgan. Augustus de Morgan, born in Madura, Madras, in June 1806 and died in London on March 18, 1871, was educated at Trinity College, Cambridge, but in the then state of the law was, as a Unitarian, ineligible to a fellowship. In 1828 he became professor at the newly established University of London, which is the same institution as that now known as University College. There, except for 5 years from 1831 to 1835, he taught continuously till 1867, and through his works and pupils exercised a wide influence on English mathematicians of the present day. The London Mathematical Society was largely his creation, and he took a prominent part in the proceedings of the Royal Astronomical Society. He was perhaps more deeply read in the philosophy and history of mathematics than any of his contemporaries, but the results are given in scattered articles as well, which well deserve collection and republication. A list of these is given in his life, and I have made considerable use of some of them in this book. The best known of his works are the Memoirs of the Foundation of Algebra, Cambridge Philosophical Transactions, volumes 8 and 9, his treatise on the differential calculus published in 1842, a work of great ability and noticeable for the rigorous treatment of infinite series, and his articles on the calculus of functions on the theory of probabilities in the Encyclopaedia Metropolitana. The article on the calculus of functions contains an investigation of the principles of symbolic reasoning, but the applications deal with the solution of functional equations rather than with the general theory of functions. The article on the theory of probabilities gives a clear analysis of the mathematics of the subject to the time at which it was written. Besides those above named, I may mention the following who have written on the subjects of higher algebra, the theory of forms, and the theory of equations. Joseph Ludwig Rabe, who in 1832 discussed the test for the convergency of series, a subject also discussed later by Joseph Louis Francois Bertrand, secretary of the French Academy, born in Paris in 1822, Kummer, Ulysse Dini of Pisa, and A. Pringsheim of Munich. And on the researches of the above writers see the Bulletin of the New York Mathematical Society, October 1892, pages 1 to 10. George Boole, born at Lincoln in November 2, 1815, died at Cork on December 8, 1864, who invented a system of non-commutative algebra and from whose memoirs on linear transformations part of the theory of covariance has developed. Évariste Galois, one of the most original and powerful mathematicians of this century, born at Paris on October 26, 1811, and then killed in a duel on May 30, 1832, at the early age of 20, whose writings are mainly concerned with the theory of equations and substitution groups. On his investigations, see Liouville's Journal for 1846, volume 11, pages 381 to 444, and the American Journal of Mathematics for 1891, volume 13, pages 109 to 142. Carl Wilhelm Borchardt, professor in Berlin, born there on February 22, 1817, died there 1880, who in particular discussed generating functions in the theory of equations and arithmetic geometric means. A collected edition of his works, edited by G. Hettner, was issued at Berlin in 1888. Cayley, whose 10 classical memoirs on quantics, binary and ternary forms, and researches on non-commutative algebras, especially on matrices, will be found in the collected edition of his works. Sylvester. From among those whose numerous memoirs I may in particular single out, those on canonical forms, on the theory of contravariants, reciprocants of differential invariants, on the theory of equations, and that on Newton's rule, to which I may add that he has created the language and notation of considerable parts of the subjects on which he has written. Camille Jordan, who has written on the theory of substitutions in general and with special applications to differential equations. Sir George Gabriel Stokes, Lucasian professor in the University of Cambridge, born near Sligo on August 13, 1819, who has written on the critical values of the sums of the periodic series and on the summation of series. Cambridge Philosophical Transactions, 1847, volume 8, pages 533 to 583. See also below, pages 492 and 496. Eugene Netto of Strasbourg, who has written on substitutions. Hermite, who has in particular discussed the theory of associated contravariants in binary quantics, the theory of ternary quantics, and who has applied elliptic functions to the solution of the quintic equation. Enrico Betti of Pisa, who died in 1892, and Brioschi, both of whom discussed binary quantics. Siegfried Heinrich Ehrenhold, born at Engerberg on July 16, 1819, who developed symbolic methods, especially in connection with ternary quantics. This was done concurrently with, but independently of, Cayley's work on the same subject. Paul Gordin, professor at Erlangen, who had discussed the theory of forms and shewed that there are only a finite number of concomitants of quantics. An edition of his work on invariants, determinants, and binary forms, edited by G. Kersteiner, was issued at Leipzig in 3 volumes, 1885, 1887, and 1893. Rudolf Friedrich Alfred Klebsch, born at Königsberg in 1833, died in Göttingen, where he was professor in 1872, who also independently investigated the theory of binary forms in some papers collected and published in 1871. An account of his life and works is printed in the Mathematische Annalen, 1873, volume 6, pages 197 to 202, and 1874, volume 7, pages 1 to 55. See also below. McMahon, who has written on the connection of symmetric functions, the derivation of invariants and the covariants from elementary algebra, and the concomitants of binary forms. Sophus Lie, professor at Leipzig, who has written on groups of continuous substitutions, differential invariants, and complexes of lines. Klein, who has investigated the problem of discontinuous substitutions in polyhedra groups. And lastly, Andrew Russell Forsyth, fellow and lecturer of Trinity College, Cambridge, born at Glasgow on June 18, 1858, who has developed the theory of invariants of differential equations, ternariants, and quaternariants. No account of contemporary writings of this subject would be complete without a reference to the admirable textbooks produced by George Salmon, provost at Trinity College, Dublin, born in 1819, in his Higher Algebra, and by Joseph Alfred Serret, professor at the Sorbonne in Paris on August 30, 1819, died in 1885, in his Cours d'Algèbre Supérieure, in which the chief discoveries of their respective authors are embodied. An admirable historical summary of the theory of the complex variable is given in the Vorlesungen über die komplexen Zahlen, Leipzig, 1867, by H. Henkel, professor at Tübingen, born at Halle in 1839 and died at Schramberg in 1873. Before mentioning the creators of modern synthetic geometry, it will be convenient to call attention to 2 other divisions of pure mathematics which have been greatly developed in recent years, but any sketch of the results arrived at or the methods by which they have been attained would be so closely connected with the work of living mathematicians that I shall do little more than mention the names of the subjects. Analytical geometry has been studied by a host of modern writers, but I do not propose to describe their investigations, and I shall content myself by merely mentioning the names of the following mathematicians. James Booth, born in the country of Leitrim on August 25, 1806, and died at Buckinghamshire on April 15, 1878, was one of the earliest writers in this century to devote himself to the development of analytical geometry. His chief results are embodied in his work entitled A Treatise on Some New Geometrical Methods. The researches of James McCulloch, professor in Dublin, born near Starbane in 1809 and died in Dublin on October 24, 1846, which include some valuable discoveries in the theory of quadrics, will be found in this collected works edited by Jellett and Houghton, Dublin 1880. See also below, page 496. Julius Plücker, professor after 1836 in Bonn, born at Elberfeld on July 16, 1801 and died at Bonn on May 22, 1868, devoted himself chiefly to the study of algebraic curves, of a geometry in which the line is the element in space, and the theory of congruences and complexes. His equations connecting the singularities of curves are well known. In 1847 he exchanged his chair for one of physics, and his subsequent researches were on spectra and magnetism. An account of his works was published by Klebsch, Gesellschaft der Wissenschaften, Göttingen, 1872, volume 16. The majority of the memoirs on analytical geometry by Cayley and by Henry Smith deal with the theory of curves and surfaces, the most remarkable of those of Ludwig Otto Hess, born at Königsberg on April 22, 1811 and died at Munich, where he was professor in 1874, are on the plane geometry of curves. See the notice of these by F. C. Klein. Of those of Jean-Gaston Darboux, professor in Paris, born at Nimes at 1842, on the geometry of surfaces, and those of Halphen on the singularities of surfaces and on tortuous curves. The singularities of curves and surfaces have also been considered by Hieronymus Georg Suthen, professor at Copenhagen, born in 1839, and by Hermann Caesar Hannibal Schubert, professor at Hamburg, born at Potsdam in 1848. The lectures of the latter have been published by F. Lindemann, 2 volumes, Leipzig, 1875 and 1891. Noether has discussed the theory of tortuous curves, and Klebsch has applied Abel's theorem to geometry. Among more recent textbooks are Klebsch's Vorlesungen über Geometrie, edited by F. Lindemann, and Selman's Conic sections Geometry of Three Dimensions, and Higher Plane Curves, in which the chief discoveries of these writers are embodied. Finally, I may allude to the extension of the subject matter of analytical geometry by the introduction of the ideas of space of n dimensions in the writings of Grossman in 1844 and 1862. Among those who have extended the range of analysis, including the calculus and differential equations, or whom it is difficult to place in any of the preceding categories, are the following, whom I place in alphabetical order: Appel, Bertrand, Boole, Cauchy, Darboux. Forsyth, who has written on Pfaff's problem and is also the author of the standard English treatise on differential equations. Frobenius, Lazarus Fuchs, professor at Berlin, born in Prussia 1833, Halphen, Jacobi, Jordan, Königsberger, Sophie Koloweski, professor at Stockholm, born on December 27, 1853 and died February 18, 1891. See the Bulletin des Sciences Mathématiques, volume 15, pages 212 to 220. Lie, Poincaré, Riemann, who wrote on the theory of partial differential equations, Schwarz, Sylvester, and Weierstrass, who has developed the calculus of variations. The writers I have mentioned above mostly concern themselves with analysis. I will next describe some of the more important works produced in this century on synthetic geometry. Modern synthetic geometry may be said to have had its origin in the works of Monge in 1800, Carnot in 1803, and Poncelet in 1822, but these only dimly foreshadowed the great extension it was to receive in Germany, of which Steiner and von Staudt are perhaps the best known exponents. Steiner. Jacob Steiner, the greatest geometrician since the time of Apollonius, was born at Utzendorf on March 18, 1796 and died at Bern on April 1, 1863. His father was a peasant, and the boy had no opportunity to learn reading and writing till the age of 14. He subsequently went to Heidelberg and thence to Berlin, supporting himself by giving lessons. His Systematische Entwicklungen was published in 1832, and at once made his reputation. It contains a full discussion of the principle of duality and of the projective and homographic relations of rows, pencils, etc. based on metrical properties. By the influence of Crell, Jacobi, and the von Humboldts, who were impressed by the power of his work, a chair of geometry was created for Steiner at Berlin, and he continued to occupy it till his death. The most important of his other researches are contained in papers which appeared originally in Crell's journal and are embodied in his Systematische Geometrie, Volume 1, edited by C. F. Geiser, Volume 2 by H. Schroeter. These relate chiefly to the properties of algebraic curves and surfaces, pedals and roulettes, and maxima and minima. The discussion is purely geometrical. Steiner's works may be considered as the classical authority on recent synthetic geometry. Von Staudt. A system of pure geometry quite distinct from that expounded by Steiner was proposed by Carl Georg Christian von Staudt, born at Rothenburg on January 24, 1798, and died in 1867, who held the chair of mathematics at Erlangen. In his Geometrie der Lage, published in 1847, he constructed a system of geometry built up without any reference to number or magnitude, but in spite of its abstract form he succeeded by means of it alone in establishing the non-metrical projective properties of figures, discussed imaginary points, lines, and planes, and even obtained a geometrical definition of a number. These views were further elaborated in his Bertrand Géométrie de l'âge, 1856 to 1860. This geometry is curious and brilliant, and has been used by Kuhlmann as the basis of his graphical statistics. Among other works on pure geometry I may refer to the Introduzione ad una teoria geometrica delle curve piane, 1862, and its continuation, Preliminari de una teoria geometrica delle superficie, by Luigi Cremona of the Polytechnic School at Rome. As usual, textbooks I may mention: M. Schalz's Traité de géométrie supérieure, 1852, J. Steiner's Vorlesungen über synthetische Geometrie, 1867, and L. Cremona's Éléments de géométrie projective, translated into English by C. Lusendorf, Oxford, 1885, and Thomas Reyes' Géométrie de l'âge, 3 volumes, 3rd edition. I shall conclude the chapter with a few notes, more or less discursive, on branches of mathematics of a less abstract character and concerned with problems that occur in nature. Closely connected with the subject of modern geometry is the science of graphics, in which rules are laid down for solving various problems by the aid of the drawing board. The modes of calculation which are permissible are considered in modern projective geometry. This method of attacking questions has been hitherto applied chiefly to problems in mechanics, elasticity, and electricity, and it is especially useful in engineering, and in that subject an average draftsman ought to be able to obtain approximate solutions of most of the equations, differential or otherwise, with which he is likely to be concerned, which will not involve errors greater than would have to be allowed for in any case in consequence of our imperfect knowledge of the structure of the materials employed. The theory may be said to have originated with Poncelet's work, but I believe that it is only within the last 20 years that systematic expositions of it have been published. Among the best known of such works I may mention are Graphische Statik by C. Kuhlmann, Zurich, 1875, recently edited by W. Ritter, and the Lesioni di Statistica Grafica by A. Favaro, Padua, 1877, French translation annotated by P. Terrier in 2 volumes, 1879 to 85, and the Calcolo Grafico by L. Cremona, Milan, 1879, English translation by T. H. Beer, Oxford, 1889, which is largely founded on Mobius's work. La Statique Graphique by M. Levy, Paris, 4 volumes, 1886–88, and La Statistica Grafica by C. Cerotti, Milan, 1888. The general character of these books will be sufficiently illustrated by the following note on the concepts of Kuhlmann's work. Kuhlmann commences with a description of the geometrical representation of the 4 fundamental processes of addition, subtraction, multiplication, and division, and proceeds to evolution and involution, the latter being effected by the use of equiangular spirals. He next shews how the quantities considered, such as volumes, moments, and moments of inertia, may be represented by straight lines, thence deduces the laws for combining forces, couples, etc., and then explains the construction and use of the ellipse and ellipsoid of inertia, the neutral axis, and the kern. The remaining and larger part of the book is devoted to shewing how geometrical drawings made up on these principles give the solutions of many practical problems connected with arches, bridges, frameworks, earth pressure on walls and tunnels, etc. The subject has been treated during the last 20 years by numerous writers, especially in Italy and Germany, and applied to a large number of problems. But as I stated at the beginning of this chapter, that I should as far as possible avoid discussions of the works of living authors, I content myself with a bare mention of the subject. End of section 36. Chapter 19. Mathematics of Recent Times, Part 4. Clifford. I may however add here a brief note on Clifford, who is one of the earliest English mathematicians of the latter half of this century to advocate the use of graphical and geometrical methods in preference to analysis. William Kingdon Clifford, born at Exeter on May 4, 1845, and died at Madeira on March 3, 1879, was educated at Trinity College, Cambridge, of which society he was a fellow. In 1871 he was appointed professor of applied mathematics at University College London, a post which he retained till his death. His remarkable felicity of illustration and power of seizing analogies made him one of the most brilliant expounders of mathematical principles. His health failed in 1876, when the writer of this book undertook his work for a few months. Clifford then went to Algeria and returned at the end of the year, but only to break down again in 1878. His most important works are his theory of biquaternions, on the classification of loci unfinished, and the theory of graphs unfinished, his canonical dissection of a Riemann's surface, and the elements of dynamic also contain much interesting matter. I next turn to the question of mechanics treated analytically. The knowledge of mathematical mechanics of solids attained by the great mathematicians of the last century may be said to be summed up in the admirable Mécanique analytique by Lagrange and Traité de mécanique by Poisson, and the application of the results to astronomy is illustrated by Laplace's Mécanique céleste. These works have been already described. The mechanics of fluids is more difficult than that of solids, and the theory is less advanced. Theoretical statics, especially the theory of potential and attractions, has received considerable attention from mathematicians of this century. I have already mentioned that the introduction of the idea of the potential is due to Lagrange, and it occurs in a memoir of a date as early as 1773. The idea was at once grasped by Laplace, who in his memoir of 1784 used it freely, and to whom the credit of the invention was formerly somewhat unjustly attributed. In the same memoir Laplace also extended to space of 3 dimensions the idea of circular harmonic analysis which had been introduced by Legendre in 1783. Green. George Green was one of the earliest writers of this century who investigated further the properties of the potential. Green was born near Nottingham in 1793 in a humble condition in life, and died at Cambridge in 1841.
Although self-educated, he contrived to get access to various mathematical books, and in 1827 wrote a paper on the potential, in which the term was first introduced, proved its chief properties, and applied the results to electricity and magnetism. This contains the important theorem now known by his name. This remarkable paper was seen by some neighbours who were able to appreciate the power shewn in it. It was published by subscription in 1828, but does not seem to have attracted much attention at first. Similar results were independently established in 1839 by Gauss, to whom their general dissemination was due. In 1832 and 1833 Green presented papers to the Cambridge Philosophical Society on the equilibrium of fluids and on attractions in space of n dimensions, and in the latter year his memoir on the motion of a fluid agitated by the vibrations of a solid ellipsoid was read before the Royal Society of Edinburgh. In 1833 he entered at Caius College, Cambridge, and was subsequently elected to a fellowship. He then threw himself into original work, and produced in 1837 his paper on the motion of waves in a canal, and on the reflection and refraction of sound and light. In the latter, the geometrical laws of sound and light are deduced by the principle of energy from the undulatory theory, the phenomenon of total reflection is explained physically, and certain properties of the vibrating medium are deduced. He also discussed the propagation of light in any crystalline medium. Of Gauss's work on attractions I have already spoken. The theory of level surfaces and lines of force is largely due to Chasles, who also determined the attraction of an ellipsoid at any external point. I ought not to leave the subject of theoretical statics without mentioning Mobius. August Ferdinand Mobius, professor at Leipzig, who was born at Schulpforta on November 17, 1790, and died on September 26, 1868, was one of the best known of Gauss's pupils. He published his Barycentrisches Calcul in 1826. His collected works were published at Leipzig in 4 volumes, 1885 to 1887. Among living writers I may allude to Sir Robert Stawell Ball, Lowndean professor in the University of Cambridge, born in Dublin on July 1, 1840, who issued his Theory of Screws in 1876. Theoretical dynamics has been studied by most of the writers above mentioned. In addition to these, I may repeat that the principle of varying action was elaborated by Sir William Hamilton in 1827, and the Hamiltonian equations were given in 1835, and I may call attention to Bertrand's work on dynamics. The use of generalized coordinates introduced by Lagrange has become the customary means of attacking dynamical as well as many physical problems. The standard English textbook on the dynamics of rigid bodies is that by Dr. Rouse. On the mechanics of fluids, liquids, and gases, apart from the physical theories on which they rest, I propose to say nothing except to refer to the memoirs of Green, Sir George Stokes, Lord Kelvin, better known as Sir William Thomson, and von Helmholtz. The fascinating but difficult theory of vortex rings is due to the 2 writers last mentioned. One problem in it has been also considered by J. Thomson, but it is a subject which is as yet rather beyond our powers of analysis. The subject of sound may be treated in connection with hydrodynamics, but on this I would refer the reader who wishes for further information to the work published at Cambridge in 1877 by Lord Rayleigh, recently Cavendish Professor in the University of Cambridge. Theoretical astronomy is included in, or at any rate closely connected with, theoretical dynamics. Among those who in this century have devoted themselves to the study of theoretical astronomy, the name of Gauss is one of the most prominent. To his work I have already alluded. Bessel. The best known of Gauss's contemporaries was Friedrich Wilhelm Bessel, who was born in Minden on July 22, 1784, and died at Königsberg on March 17, 1846. Bessel commenced his life as a clerk on board ship, but in 1806 he became an assistant in the observatory at Lilienthal, and was thence in 1801 promoted to be director of the new Prussian observatory at Königsberg, where he continued to live during the remainder of his life. Bessel introduced into pure mathematics those functions which are now called by his name. This was in 1824, though their use is indicated in a memoir 7 years earlier, but his most notable achievements were the reduction, given in his Fundamenta Astronomiae (Königsberg, 1818), of the Greenwich observations by Bradley of 3222 stars, and his determination of the annual parallax of 61 Cygni. Bradley's observations have been recently reduced again by Dr. A. Auwers of Berlin. Leverrier. Among the astronomical events of this century the discovery of the planet Neptune by Leverrier and Adams is one of the most striking. Urbain Jean-Joseph Leverrier, the son of a petty government employee in Normandy, was born at Saint-Lô on March 11, 1811, and died at Paris on September 23, 1877. He was educated at the Polytechnic School, and in 1837 was appointed as lecturer on astronomy there. His earliest researches in astronomy were communicated to the Academy in 1839. In these he calculated, within much narrower limits than Laplace had done, the extent within which the inclinations and eccentricities of the planetary orbits vary. The independent discovery in 1846 by Leverrier and Adams of the planet Neptune, by means of the disturbance it produced on the orbit of Uranus, attracted general attention to physical astronomy, and strengthened the opinion as to the universality of gravity. In 1855 Leverrier succeeded Arago as director of the Paris Observatory, and reorganized it in accordance with the requirements of modern astronomy. He now set himself the task of discussing the theoretical investigations of the planetary motions, and of revising all tables which involve them. He lived just long enough to sign the last proof sheet of this work. Adams. The co-discoverer of Neptune was John Couch Adams, who was born in Cornwall on June 5, 1819, educated at St. John's College, Cambridge, subsequently appointed to Lowndean professor in the university, and director of the observatory, and who died at Cambridge on January 21, 1892. There are three important problems which are especially associated with the name of Adams. The first of these is his discovery of the planet Neptune from the perturbations it produced on the orbit of Uranus. In point of time this was slightly earlier than Leverrier's investigation. The second memoir to which I referred was on the secular acceleration of the moon's mean motion. Philosophical Transactions, 1855, volume 143, page 377. Laplace had calculated this on the hypothesis that it was caused by the eccentricity of the Earth's orbit, and had obtained a result which agreed substantially with the value it deduced from a comparison of the records of ancient and modern eclipses. Adams shewed that certain terms in an expression had been neglected, and that if they were taken into account the result was only about one half that found by Laplace. The correctness of the calculations of Adams was denied by Plana, Pontécoulant, and other continental astronomers, but Delaunay in France and Cayley in England verified the work. The third investigation connected with the name of Adams is his determination of the orbit of the Leonids or shooting stars, which were especially conspicuous in November 1866, and whose period is about 33 years. Newton of Yale had shewn that there were only 5 possible orbits. Adams calculated the disturbance which would be produced by the planets on the motion of the node of the orbit of a swarm of meteors in each of these cases, and found that this disturbance agreed with the observations for one of the possible orbits, but for none of the others. Hence the orbit was known. Other well-known astronomers of this century are Giovanni Antonio Amadeo Plana, born at Voghera on November 8, 1781, and died at Turin on January 20, 1864, whose work on the motion of the moon was published in 1832. Philip Gustav Durchet, Count Pontecolon, born in 1795 and died at Pontecolon on July 21, 1871. Charles Eugène Delaunay, born at Lausigny on April 9, 1816, and drowned off Cherbourg on August 3, 1872, whose work on the lunar theory indicates the best method yet suggested for the analytical investigations of the whole problem, and whose incomplete lunar tables are among the astronomical achievements of this century. And Peter Andrew Hansen, born at Schleswig on December 8, 1795, and died at Gotha, where he was head of the observatory on March 28, 1874, who compiled the lunar tables published in London in 1857, and celebrated the most delicate methods yet known for the determination of lunar and planetary perturbations. For an account of his numerous memoirs, see the Transactions of the Royal Society of London for 1876 to 1877. Among living mathematicians I may mention the following names. Felix Tisserand of Paris, born in 1845, whose Mécanique Céleste forms a worthy pendant to Laplace's work of the same title. George William Hill, born in New York in 1838 and until recently on the staff of American Ephemeris, who in 1884 determined the inequalities of the moon's motion due to the non-spherical figure of the earth, an investigation which completed Delaunay's lunar theory. Hill also dealt with the secular motion of the moon's perigee and the motion of a planet's perigee under certain conditions, and he has written on the analytical theory of the moon of Jupiter and Saturn with a view to the preparation of tables of their positions at any given time. Simon Newcomb, born in Nova Scotia on March 12, 1835, superintendent of the American Ephemeris, who re-examined the Greenwich observations from the earliest times, applied the result to the lunar theory, and revised Hansen's tables. George Howard Dowron of Trinity College, Cambridge, born in Kent in 1845, now Plumian professor in the University of Cambridge, who has written on the effect of tides on viscous spheroids, the development of planetary systems by means of tidal friction, the mechanics of meteoric swarms, etc. Perhaps also I may here mention Poincaré, who has discussed the difficult problem of three bodies and the form assumed by a mass of fluid under its own attraction. Within the last half century the results of spectrum analysis have been applied to determine the constitution and directions of motions of the heavenly bodies to and from the earth. The early history of spectrum analysis will be always associated with the names of Gustav Robert Kirchhoff and A. J. Angstrom of Uppsala and Sir George Stokes of Cambridge, but it pertains to optics rather than to astronomy. Within the last few years the range of astronomy has been still further extended by the art of photography. To what new developments this may lead it is as yet impossible to say. Mathematical physics. An account of the history of mathematics in this century would not be other than misleading if there were no reference to the application of it to numerous problems in heat, elasticity, light, electricity, and other physical subjects. The history of mathematical physics is, however, so extensive that I could not pretend to do it justice even were its consideration properly included in a history of mathematics. Moreover, it is so closely connected with the works of living physicists, notably of von Helmholtz and of Lord Kelvin, better known as Sir William Thomson, that I may consider it outside the limits I have laid down for myself in this chapter. It is however interesting to note that the advance in our knowledge of physics is largely due to the application to it of mathematics, and every year it becomes more difficult for an experimenter to make any mark on the subject unless he is also a mathematician. Amongst recent writers on mathematical physics, excluding all reference to experimental physics, as also to theories to which mathematical analysis has not yet been applied, I may specially mention the following, whose names are here arranged alphabetically, though the list does not in any way profess to be complete or exhaustive. J. Boussinesq of Paris, who has written on optics. Ludwig Boltzmann of Vienna, whose writings greatly extended the kinetic theory of gases and have done something to bring the molecular physics within the domain of mathematics. Rudolf Julius Emanuel Clausius, born at Köslin on January 2, 1822, and died at Bonn, where he was professor of physics in August 1888, who was among the earliest to discuss the subject of heat from a mathematical point of view. Clebsch, who discussed the elasticity of solid bodies. Julius Wilhelm Richard Dedekind, who is the author of a remarkable memoir on the vibrations of a liquid ellipsoid, which is treated as a problem in pure mathematics. Michael Faraday, born at Newington on September 22, 1791, and died at Hampton Court on August 25, 1867, who had a special gift in deducing results by general reasoning from fundamental principles, and in disentangling those principles from the symbols in which they are usually expressed. For further details, see the biographies of Tyndall, 2nd edition 1870, Bence Jones 1870, or Dr. Gladstone 1872. George Francis Fitzgerald, professor in Dublin, born there on August 3, 1851, who has written on electromagnetism and optics. John Bernard Léon Foucault, born at Paris on September 18, 1819, and died there of paralysis on February 11, 1868, whose chief memoirs were on the predictability of photography 1840, on the electric lamp 1849, on the determination of the velocity of light in 1850, but repeated with improvements in 1862, on his demonstration of the diurnal motion of the earth by means of the rotation of the plane of oscillation of a simple pendulum 1851, on the gyroscope 1852, on the rotation of a copper disc between the poles of a magnet 1855, and on a polarizer 1857. For further details, see La vie et travaux de Léon Foucault by J. A. Lycejus, Paris, 1875, and also a notice by J. Bertrand, preface to the collected edition of Foucault's works, Paris, 1878. J. Willard Gibbs of Yale, America, who has written on the thermodynamics and Maxwell's electromagnetic theory. Richard Tetley Glazebrook of Trinity College, Cambridge, born at Liverpool on September 18, 1854, who has written on optics and electricity. His report in the Transactions of the British Association 1885 on theories of optics contains a valuable summary of most of the mathematical researches on that subject during this century and prior to the date of the report. After a brief allusion to the views of Green, Cauchy, McCulloch, and F. E. Newman, he describes the more recent work according as it comes under the simple elastic solid theory, or theories assuming an action between matter and ether, or Maxwell's electromagnetic theory. Green, whose physical memoirs were mostly on the theory of waves. Von Helmholtz, who is in the front rank of all departments of mathematics and physics. His collected papers were published in 2 volumes, Leipzig, 1882 to 1883. Oliver Heaviside, who has written on the mathematical theories of optics and electromagnetism. Lord Kelvin, or Sir William Thomson, professor at Glasgow, born at Belfast, June 1824, who has enriched every department of physics by his researches. His collected papers were published at Cambridge, Volume 1 in 1882, and Volume 2 in 1884, and Volume 3 in 1890. Gustav Robert Kirchhoff, professor in physics, first at Heidelberg and then at Berlin, born at Königsberg on March 12, 1824, and died in Berlin October 17, 1887, whose name will always be associated with the history of spectrum analysis and his researches on elasticity. His collected papers were published at Leipzig in 1882. Gabriel Lamé, born at Tours on July 22, 1795, and died at Paris in 1870, where he was professor at the Polytechnic School, whose best known works are his Course on Physics, 1836, his Treatise on Elasticity, 1852, his work on Functions, 1857, an essay on the curvilinear coordinates, 1859, and lastly his Theory of Heat, 1861. He also wrote memoirs on different points in the theory of numbers. James Clerk Maxwell, born at Edinburgh on June 13, 1831, and died at Cambridge on November 5, 1879, where he was professor of experimental physics. His most important works were his memoir in 1859 on the stability of Saturn's rings, various articles on color, his memoir on the electromagnetic field, his Electricity and Magnetism issued in 1873, his Theory of Heat published in 1871, and his elementary textbook on matter and motion. To these I may add his memoir on reciprocal figures, which are useful in graphics, and his papers on molecular theory of gases and cognate subjects. His Electricity and Magnetism has revolutionized the treatment of the subject. Poisson and Gauss had explained the phenomenon of electrostatics by attraction and repulsions between imponderable particles, while Lord Kelvin, Sir William Thomson, in 1846 has shewn that the effects might be supposed analogous to a flow of heat from various sources of electricity properly distributed. In electrodynamics, the theory then generally current was that proposed by W. E. Weber, in which the attraction between electrified particles depends on their relative motion and position. Maxwell rejected all these hypotheses and explained the phenomenon by stresses and motions of a material medium. He concluded by shewing that if the medium were the same as the so-called luminiferous ether, the velocity of light would be equal to the ratio of the electromagnetic and electrostatic units. Subsequent experiments have tended to confirm this conclusion. For fuller details, his collected works, Cambridge, 2 volumes, 1890, and his Life by L. Campbell and W. Garnett, London, 1882, may be consulted. McCulloch, who wrote on physical optics. Franz Ernst Neumann of Königsberg, born at Uckermark on September 11, 1798, who wrote on elasticity and light. William John Rankine of Glasgow, born at Edinburgh on July 5, 1820, and died December 24, 1872, whose discoveries in thermodynamics and hydromechanics will be found in the collected edition of his works issued in London in 1881. Lord Rayleigh, born on November 12, 1842, who, besides some classical papers on the mathematics of physical optics, has written the standard English work on sound, published at Cambridge in 1877. Barré de Saint-Venant, whose researches on elasticity and torsion are well known. Sir George Gabriel Stokes, most of whose papers on hydromechanics or optics or allied subjects, these memoirs have been recently collected and published by the University of Cambridge. Peter Guthrie Tait, professor in Edinburgh, born at Dalkeith on April 28, 1831, who has written on the mathematics of various physical subjects, and especially on the molecular theory of gases. Joseph John Thomson, of Trinity College and Cavendish professor in the University of Cambridge, born at Manchester on December 18, 1856, who has written on vortex rings and the application of generalized coordinates to various physical problems. I may also allude to his report on the Transactions of the British Association, 1885, on electric theories, which he classifies into those not founded on the principle of conservation of energy, such as those of Ampere, Grassmann, Stefan, and Korteweg; those which rest on assumptions concerning the velocities and positions of electrified particles, such as those of Gauss, W. E. Weber, Riemann, and Clausius; those which require the existence of a kind of energy of which we have no other knowledge, such as the theory of C. Neumann; those which rest on the dynamical considerations but in which no account is taken of the action of the dielectric, such as the theory of F. E. Newman; and finally those which rest on the dynamical considerations and in which the action of the dielectric is considered, such as Maxwell's theory. In the report these theories are described, criticized, and compared with the results of experiments. Wilhelm Eduard Weber died in 1891, whose most important investigations were in connection with electrodynamics. His works are being produced by the Royal Society of Göttingen, Volume 1, edited by W. Voigt, Berlin, 1892. And Gustav Heinrich Wiedemann of Bale, born October 2nd, 1826, who is the author of an admirable textbook on electricity and allied subjects, 4 volumes, 1882 to 1885. I am well aware that the above list excludes many who have studied physics from a strictly mathematical point of view, and I give it not as an account of a contemporary work, but as a pendant to this chapter, which may serve as an indication of the subjects discussed by many mathematicians in recent times, illustrated by the names of a few of them. To make it more than this would involve the knowledge to which I can make no pretence. End of Part 37. This is the end of a short account of the history of mathematics by W. W. Rouse.